four, three, two, one.
Welcome to NASA Science Live. I'm your host, Joy Ng. Today, we are going to talk to NASA experts about the sun, its incredible influence across our solar system, and a NASA mission that recently launched to study sun-induced electric currents that flow high above Earth's poles. This is your chance to interact with NASA experts and have your questions answered in real time. So be sure to send in your questions using the hashtag AskNASA in the comments wherever you're watching. NASA's Electrojet Zeeman Imaging Explorer, or EASY for short, is the first mission to measure the magnetic fingerprints of the Aurora electrojets up close and in detail. The electrojets are central to the electrical circuit that connects Earth's magnetosphere to its atmosphere. The EASY mission is part of NASA's heliophysics division, which studies the sun as well as its influence on Earth and the entire solar system. The EASY mission launched just a few days ago on March 14th with liftoff at 11:43 p.m. Pacific time from Vandenberg Space Force Base in California. EASY launched aboard a SpaceX Falcon 9 rocket as part of the Transporter 13 rideshare mission via launch integrator Maverick Space Systems. At approximately 2 a.m. Pacific time on March 15th, the EASY satellites were successfully deployed. You can see that happening here. The 3 EASY satellites were deployed into orbit one by one to fly in formation around Earth's polar regions. And last week, the spacecraft sent signals to the ground to verify they are in good health and are operating normally. During their 18th month mission, EASY's trio of CubeSats will map the Aurora electrojets to uncover their structure and evolution. Aurora electrojets are these intense electric currents that are part of the aurora, which are sparked by the sun's activity. They can be responsible for large magnetic disturbances on the ground that can affect things like power lines and transformers. So I have 2 guests with me today who can tell us more about the EASY mission, the activity on the sun. And so with us now is Dr. Larry Kepko, who is the EASY mission scientist from NASA, and Dr. Nelly Masava-Hoya, who is the EASY mission program manager from the Johns Hopkins Applied Physics Laboratory. Thank you so much for joining me.
My pleasure.
Of course. Thanks for having us.
So can you start by explaining a little bit about your roles? Nelly, why don't you go first?
Sure, yeah. So as you mentioned, I'm the program manager for EASY mission. I have a very exciting job. My job is basically to make sure that the mission is successful. In every NASA mission, the scientists, they decide where they want to go, which planet they want to visit, what kind of data they want to collect. And then the engineers, they help with bringing that vision to reality. They make the spacecraft, the instrument, the systems, how we get there, what kind of data to collect. And my job is to make sure that the engineers and the scientists, they work together nicely and they have all the resources that they need, the technical resources, financial resources that they need to make sure that the mission is successful. We understand as a team what kind of risks exist and make sure that we can resolve and mitigate those risks. And also my job is to make sure that we are on cost and schedule. And at the end, the mission, not only we provide the scientific data that we promised NASA, but also stay on cost and schedule and the mission is successful at the end.
And what about you, Larry?
And I'm what's called the mission scientist. I am a NASA civil servant, so I work for the federal government. My primary responsibility in that role is that every stage of the mission, from when it's formulated to design, integration, testing, all the way through launch and through the end of the mission, is I'm a steward of the taxpayers' investment in the mission. As a civil servant, that's my responsibility. Now, this mission went through a very rigorous competition, and once it was selected, the mission committed to solving a specific science question. In this case, solving the mysteries of the Aurora electrojets. I serve as an independent set of eyes and ears Nellie works with the team to make sure that on a daily basis they're doing what they're supposed to be doing to get the spacecraft up and out. And I'm there to watch just to make sure that if something happens or changes are made, something goes wrong, that we're still capturing the science that we need to capture. Now, thankfully, EASY didn't really have any issues going through the whole development process. So my job was fairly easy. But in the end of the day, we just simply are there to watch and make sure we maximize and the science return for the taxpayer.
Thank you both. So let's get into today's main topic, which is EASY. I mentioned earlier that this mission is going to study auroral electrojets. These are the electric currents near Earth's polar regions that are present when auroras glow in the sky. So can you tell me why scientists are interested in studying this area? Larry?
Right. So, Sorry. So I am a card-carrying auroral scientist. I have a PhD in space physics. I work here at Goddard Space Flight Center in the Heliophysics Science Division. Heliophysics is the study of the sun and its interaction through all objects in the solar system. Now, what you see behind us is a picture of the aurora, probably from the International Space Station. And that's exactly what EASY is going to study. EASY will study the currents that flow through these aurora, as you can see here. Now, within these aurora, we have electrical currents. And these electrical currents flow just 70 miles above our head, which is pretty amazing if you think about it. If you could drive there straight up, it would take you about an hour to get this very exciting dynamic region. Now, within these aurora, the currents flow just like currents you have at home when you plug something into the wall, a current flows in your wire. It's the same sort of process that happens in space. These currents flow because of the interaction with the sun and the solar wind. The solar wind is that stream of particles that come from the sun on a daily basis, and how they interact with Earth's magnetic field. And the interaction causes currents to flow throughout the ionosphere, that layer just above our heads. Now, these currents push about 1 million amps of currents through the ionosphere. Just to put that in perspective, if you're not familiar with how much current that is, a typical household appliance like your refrigerator, your hairdryer, things like that, might be just a few amps. And if you've ever had your circuit breaker trip, you might have drawn 15 or 20 amps. And yet here, just above our head, again, just an hour above our head by car, we have 1 million amps flowing ahead. And that's really quite neat. And to have them also associated with the aurora is super exciting as well, because the aurora is so beautiful. And there are a lot of questions about these currents, their structure, how they form and they grow and they just dissipate over time, questions that we don't have answers to, questions with great societal relevance. And it's these questions that EASY is going after.
That is very cool. So I am curious, how will these 3 individual spacecraft operate together to collect measurements?
Yes, well, I can help answering that a little bit. So we have 3 small CubeSats. They are about the size of a suitcase, so they are not that big. They are following a sun-synchronous orbit. Each orbit, it's about 90 minutes. So each spacecraft has 16 orbits in 24 hours. And we have 3 spacecraft. So we have 48 times that we can make measurements in a day. So we are providing already a lot of science data to our scientists, and they are very excited. These spacecrafts are 2 to 10 minutes separated from each other. And I actually have a small model of a CubeSat. This was built by students in Little Caesars in Arizona. So I want to thank them for making these CubeSats. And these 3 CubeSats, they follow each other in an orbit, and they don't have a propulsion. It's very neat the way that we manage to get them slower or faster. It's by changing the orientation of their solar panels. So this way it makes it go slower. This way it makes it faster. So it's a lot of engineering to make decisions how to fly these 3 spacecraft to make sure that the separation between of them is 2 to 10 minutes away from each other. Then each spacecraft has a very smart instrument. That the instrument, it's called microwave electrojet magnetometer. That it's the instrument that we had collaborated with our friends at JPL to build. And these instruments are constantly, they have 4 channels that are looking at the vibration of oxygen molecule, the emission of oxygen molecule at 118 gigahertz. This is a very well-known phenomenon that oxygen, emits at 118 gigahertz. So if you have, for example, a very good instrument like a spectroscope, you can see that emission line of the oxygen. Then in presence of magnetic field, that oxygen, the 118 gigahertz, can split. And that's really the amount of the split. It depends on how much they are introduced to magnetic field. So we have all the information about the magnetic field, and based on that, we can go backward because magnetic field and the currents are related to each other. And we do a backward calculation, and we found that all those high intense currents that Larry just talked about it, and we will map and image them for the first time. So this is a very new technique. This is for the first time that we're using this technique with 3 CubeSats. And, as I mentioned, we have a lot of data because each spacecraft has 4 channels. So our scientists are going to be super busy for the next 18 months to analyze all those data and give us the map of our electrojets. Larry, anything that you want to add?
That was a very thorough answer, Nellie. I think that's good.
So we have, charged particles coming from the sun all the time that can also create space weather events at Earth if they're directed towards us. So how will the EASY mission help in the prediction of space weather?
Yeah, EASY will really help quite a bit in terms of space weather. As you mentioned, we are constantly bombarded by activity from the sun, through the photons, through the solar wind, through particles, and they're constantly driving types of space weather. There are various types of space weather that we have to deal with. One, of course, you might be familiar with is the radiation belts, the Van Allen belts that surround Earth all the time. The space station is sort of in that regime where they have to take care of that and be aware of it. If we're going to the moon and the Mars with people, they need to be very well aware of the kind of space weather effects you get when you leave our protective bubble. And now here in our protective bubble of Earth, we are mostly safe, except for one thing. These currents that are flowing high above our head can cause, perturbations on the ground, really tough perturbations that are tough to deal with. So on Earth, we have 1 million amps flowing above our head, just 60 miles above our head. And any current that flows produces a magnetic field. We know that. We measure the magnetic field on the ground all the time. EASY is measuring that magnetic field, but remotely. Now, when a magnetic field is constant, no problem. We can handle a constant magnetic field. But when that magnetic field changes very rapidly, you induce a current somewhere else. So you might be familiar at home. Everyone, you have a phone now where you can charge remotely. You put on a little magnet and charge it remotely, or a toothbrush, something like that. That's the same process that happens in space. You're charging that remotely by changing the magnetic field. You drive a current in the other system, and that current then charges your phone or charges your battery and so on. Same thing happens here. So we have 1 million amps of current that might be changing right above our heads. That drives currents on things on the ground like power lines, power grids, sensitive electronics. And especially during strong events when things move southward, where we're not used to it, that can cause issues. In fact, there's a very famous event from 1859, the Carrington event, the largest storm we've ever seen. And in that storm, at least anecdotally, back when we had telegraph operators, he had miles and miles of long wires. And all that activity moved south. The high activity in the auroral zone created currents that flow along those telegraph wires and actually cause them to burn and spark. Now you can imagine doing that in today's society. You don't want that to happen. You could burn out power grids and things like that. So understanding how that happens is actually one of the primary goals of EASY.
Wow, it sounds like EASY will be incredibly useful. So last year there were these big aurora events that appeared farther south than what is typical. Can you explain, why that occurred?
Yeah, so as Larry mentioned, the sun is very active and constantly sending to space these high energy particles. These high energy particles, they can travel up to 1 million miles per hour, so very, very fast. And we're very lucky on Earth that we have the Earth's shield that it shows in this picture that is protecting us, and also the atmosphere. But on the North Pole and South Pole, where the field lines curve inward, it's where the field it's a little bit less. And these high energy particles, they can sneak in from the North Pole and South Pole. And when they hit the oxygen and nitrogen, they give this beautiful, colorful green color and pink colored aurora. And, every also sun has a cycle, solar cycle. And last year, and even right now, we are on the the high peak of the solar cycle. So sun is always active, but it's even more active, and we're actually very happy about that because we are in the right time and right spot to make these measurements as the sun is very active. And when the sun is very active, these high energy particles can sneak even further toward the south. And last year we saw aurora even as south of Arizona and Texas. So that's a very exciting time for the scientists that they are seeing the sun is this active, and EASY has launched on the right time.
That's fascinating. And it was also an exciting time for anyone that witnessed them as well. So is there any way for people who spot auroras to let NASA know?
Yeah, so you can go to science.nasa.gov/citizenscience. Some text may pop on the screen here in a minute. Within there you go. Within there's something called Aurorasaurus. Aurorasaurus is a little button that you scroll around. You can report your own auroral sightings, and they will then go out to the network of citizen scientists, Aurora. And it's really important to have citizen scientists. You know, NASA, we're a pretty large agency, but we can't be everywhere all at once. In particular, during large events like we just had, those aurora, that activity moves south. Like we have designed our instruments to measure the aurora where they occur normally, which funnily enough is not at the North or South Pole. It's actually the worst place to be. You would not ever see aurora at the North Pole. What you see is aurora in a band. It's called the auroral oval, and it goes through middle of Canada, through Finland, Scandinavia, Iceland, and so on. And yet during extreme activity, it pushes south to, you know, Florida, Arizona, and so on. You see it here, that sort of green line there, that circle, that's the auroral oval. That's where you see aurora. And you can imagine that just moving southward to lower latitudes. Now, when it moves southward to lower latitudes, all of our instrumentation, at least on the ground, can't see it. We can't actually measure that anymore. And so we rely on citizen scientists to help us out. Now, I was just talking just a few weeks ago to a citizen scientist in Canada who designs his own instrumentation, this beautiful, amazing instrumentation that captures the aurora. And he had gone out last year for this giant storm and put his arrays out. And he found all the aurora went south of him. He didn't see anything. He had to look far south and just saw the tops of the aurora that was over the United States. Now, everybody has a cell phone camera now, and these cameras are really quite remarkable, and they can capture the beautiful imagery of the aurora. And so people can capture that. You can go online, you can submit your photos, and they then become part of the science archive that we use to analyze our science.
Thank you. So there is another way you can participate with this mission specifically that we'll talk about in a few minutes. So stay tuned. But for now, we have a lot of questions coming in online. And remember, you can submit yours by commenting on the stream wherever you're watching or by using the hashtag AskNASA. So let's jump in. Our first question is from Sam Bird on X, and they ask, how much energy do the auroras produce?
Larry, I think this question is yours.
It's a good question. I'd have to get out my calculator and do the math. I wasn't quite ready to do P equals, yeah, I don't have a good answer for that. I guess maybe we could follow up on that, or I could do some math during a little break.
Okay, sounds good. So our next question is a viewer on YouTube, and they ask, how exactly does the mission work?
How does the mission work? So the mission, as we talked about it, it's really to understand and map the aurora electrojets for the first time. And how we are doing that, we are sensing the oxygen molecule. We talked about that the oxygen molecule emits the emission line at 118 gigahertz, and in the presence of magnetic field, those emission lines get split. And we look at those splits, and based on that, we understand how much magnetic field we have, what's the direction of it, what's the intensity of it, and then we will work backward and map the current. So that's from the science perspective, and from the engineering perspective, it's really those three CubeSats that are on the picture behind you. They do the magic. They have these very smart instruments that they constantly make measurements, each of them 16 times per day. So I hope that answered the questions, or if Larry wants to add anything.
No, but I did get out my calculator and figured it out, the number of how much.
Awesome.
It's about 100 billion watts. Remember, we have 1 million amps of current flowing overhead. Typical appliance, it's a few amps. You might think of a light bulb. The old style light bulb would be 100 watts. We have 100 billion watts of energy flowing overhead in a typical auroral display.
Wow, that is impressive.
A lot. Yeah, it's a lot. It's a lot of energy up there.
Yeah. Okay, so our next question is from Chrissy on YouTube, and they ask, will the EASY spacecraft take images of the aurora?
Yes, images, but it's not with the camera. So it's a very unique measurement that we are doing. We are, mapping by measuring the magnetic field. So we'll have an image, but it's not the typical image that we are familiar with the cameras. But it's a really interesting question.
Yeah, it's really an image of the currents that we've been talking about. You know, when you take a picture with your camera, you capture the photons and you capture the aurora. What we're taking an image of really is the currents that are flowing in the ionosphere by measuring the magnetic field. And there's some fancy math that we invert it and produce a beautiful map. So the data product we produce from EASY is actually sort of like an image in a way of the currents flowing in the ionosphere.
Fantastic. So I want to take a moment to tell our viewers about a cool project the EASY team is working on to get the public involved in the mission. The team is sending around 700 devices called magnetometers to learners across the United States. So let's take a look at how you can help scientists better understand the sun's effects on Earth using these instruments.
The auroras, or northern and southern lights, have fascinated people for millennia. Many cultures have formed traditions around these mysterious dancing lights in the sky, but hidden within them are secrets of the link between Earth and the sun. A link that scientists want to better understand so they can predict and therefore protect our technology from the impacts of space weather. Particles and energy from the sun, which reach Earth through the solar wind, interact with invisible electric currents in our atmosphere, creating dazzling auroral light shows. But if strong enough, they can also disrupt technologies like GPS satellites, communication systems, and power grids. To study the electrical currents, NASA is launching EASY in 2025. The mission will put 3 small satellites called CubeSats in orbit around Earth to create maps of these electrical currents for the first time. And you can help. Learners can join our team by becoming citizen scientists. What's a citizen scientist? They are members of the public, like you, who collaborate with professional scientists by helping collect data about our world. And they make a big impact. Intimidated? Don't be. Our EASY Magnetometer Maker Kit, called EasyMag for short, provides everything you need to participate and can be used by learners of all ages. Just like a professional engineer, you will build an instrument to collect valuable information about the world around you over the course of a year. Your data will provide essential context for the measurements that EASY satellites are making high above, helping them map the electrical currents. Educational activities and design challenges, which we provide, will help learners make EasyMag their own. Learners will be able to connect with EASY researchers through interactive webinars and even connect with each other through our global Pen Pal program. Reach out to learn more about joining the EasyMag community and helping scientists protect our technology and our planet.
What a wonderful project to get the public involved. So Nelly, you have an EasyMag with you right now. Can you tell us more about the device?
Sure. So we are very excited about this project. As you mentioned, this is for the first time that we are providing opportunity for the students to be scientists and help the scientists alongside the EASY mission scientists. So this is a magnetometer. It's actually very good grade magnetometer, and Larry will talk about that and his experience with this magnetometer. But the magnetometer, it really helps. It's a scientific instrument that helps the strength, direction, and any changes in magnetic field that you can measure with this magnetometer. So our scientists are measuring the magnetic field from the above, and the students, they can make the measurements from the ground and submit all their data to the EASY website. So the scientists will use that. So this is very valuable to be part of this project. And also it's very easy to use. It has all the components that a real magnetometer will have. It has a GPS, it has a real-time clock, it has a single board computer, it has sensors to measure the magnetic field, the orientation, and all of it comes with the very easy instructions in the Easy Mag website. So please look at this. If you're a school or you're interested, join and be part of the Easy family. And I believe, Larry, you've used this. Maybe you can talk more about how easy it is to use this Easy Mag.
I was part of the original beta test program. Just when we developed a handful of them in about a year and a half ago or so. I was able to put it together with my son. He was 10 at the time. No problem putting it together. It took about an hour. I have a little time lapse of it, putting it together, plugged it in, and it worked. And we have it sitting in our backyard today. We show it to people when they come over. I've had the associate administrator over to my house, and she's seen it in our backyard, see it operating. And I remember just a few weeks after we had initially installed it, we had one of these giant solar storms come and hit the Earth and compress the Earth. If you remember what I said about currents flowing and producing a magnetic field, well, there's a current that surrounds our magnetosphere, and that current got closer to us. And because the current was closer, we measured a stronger magnetic field. And I actually measured that with my Easy magnetometer on the ground. And I remember taking a picture of it. I had it on the screen. I took a picture of it, compared it with the proper USGS magnetometer from Virginia, and they were just almost identical. And I really excitedly texted the science team and said, look, we can do science in our backyard. So it's actually a really wonderful little project.
And I just want to also acknowledge Rob Barnes and Dr. Jasper Gallo for their support and their hard work to develop these magnetometers, and they've been a big part of the Easy family.
What an amazing project. So I hope some of the viewers today will get involved. You can learn more on easymag.jhuapl.edu. Okay, so let's get into a few more questions that are coming in online. We have our next question from Chris Street on YouTube, and they ask, will this help predict solar storms more accurately?
Do you want me to go, Ella? You want to take it?
You go ahead.
Okay. So there's different aspects of what we call solar storms. Typically, when you say the word solar storm, we think about something that erupts from the sun, or coronal mass ejection. So anytime you've seen the beautiful pictures from STO, or STOHO, or Stereo, and you see the giant, complex thing that blows off the sun and comes towards us, that's a coronal mass ejection. And that's the thing that hits us maybe 2 to 3 days later and causes what we call geomagnetic storms when it reaches the Earth. So EASY will not help predict the eruption of the coronal mass ejection, but what we will be able to predict on our side is what happens when it comes here. So I mentioned earlier the currents flowing overhead and causing perturbations on the ground. We call those geomagnetically induced currents, or GICs. And we don't really understand very well how and when they occur or how to predict their intensity. EASY will help with that for sure. We'll be flying over those structures that create GICs. And by understanding what causes their evolution, how they evolve, their intensity, we'll be able to feed that into models, which then maybe, hopefully, will help with prediction of GICs and space weather effects.
And just to add to what you, Larry, very beautifully explained, even the Easy Mag will help with that too, because now for the first time, we have 700 magnetometers that are making these measurements. And when you have 700 good data, the amount of testing, and even you can use it for data trending and prediction, that's just a lot of help to our scientists as well.
Definitely. Okay, so our next question is from Dora on X, and they ask, how do you control the satellites?
That's a really good question. So this spacecraft, as I mentioned, they are very small and they don't have a propulsion. So the way that we control them, it's by ordering or commanding the spacecraft that which direction we want the solar panels to be. So we can make them go faster or a little slower, but it's really by controlling the solar panels on the spacecraft that we control the spacecraft. And, they are in a very solid orbit right now. And, this movie shows very nicely that how we are, when it's looking upward, it's calibrating. Right now, it's making measurements. When it's in the green area, the aurora, after it comes off the aurora, we do another calibration. And after the calibration is completed, this is the area that we control the spacecraft to make sure that we maintain the 2 to 10 minute separation between the spacecraft.
Is it possible to pull that video up again? Because I want to explain something that I didn't actually understand until I came and worked at NASA. It has to do with something called reaction wheels on a spacecraft. So you look at the spacecraft, it's straight, and then look how it rotates. The way it rotates is actually quite ingenious. It has a little wheel inside. It actually has several wheels, one for each axis. And if you want to spin it like this way, this direction, you can't see my hand, but you spin it that direction, you spin the wheel the other direction. You put momentum in the other direction, the spacecraft wants to spin the opposite direction. It's as simple as that. You just have little wheels that spin one direction, the spacecraft moves the opposite direction. And it's just called reaction wheels. It's a very ingenious, simple technique for controlling spacecraft.
That's fascinating. So we have another question on YouTube. And the question is, how do you expect solar maximum to affect this mission?
I think it will work in our benefit because, what we are looking at, it's the events that are happening and how just this evolution of the current is changing. And with sun being active, I think we'll have more opportunity to make the science collections that we want. I think the T13, it's at the right time, the right season, because we're very interested in understanding the summer solstice. And now the sun is active. So a couple components are working in our favor to make sure that we have very good science data collection that help us to unlock this mapping and imaging of our electrojet.
So you mentioned T13. Can you explain a little more what you mean by that?
Oh, yes, the T13, it was the Transporter 13, the beautiful picture of the launch that you showed. So we were a share ride. How we launched was actually 74 payloads were on that spacecraft. And it's very amazing that how much the technology has changed over the last couple of years. Before the maximum, you could deploy 1 or 2 spacecraft, and it was very costly. Now with this technology, the SpaceX and a lot of launch provider satellites provider like Maverick Space System, that they have these nice dispensers that you put the satellite inside that, and it's like a suitcase that keeps you safe because the launch, it has a lot of vibration. So this dispensers that it's open, it kind of keep your satellite safe, and when it gets to the orbit that it likes, they will deploy you. So I think there was 2 different orbits for deployment. And we were deployed at 590 kilometers. So yes, it's the Transporter 13 that how we were launched with Falcon 9.
So Melody on YouTube asks, how would a present day Carrington event affect our communication satellites?
Yeah, it wouldn't be great. There's a couple things that we worry about. One are the GICs, the currents that flow in the atmosphere and produce different currents on the ground. There's a famous recent event, 1989 in Quebec, during not a huge storm, not even close to the Carrington event, that knocked out the hydroelectric plant in Quebec. And so we do worry. A Carrington event that hit at the wrong time could really destroy many transformers, knock out our power grids. It's really quite a concern. Also, satellites. They live in this environment out there, especially with particles. And now we've come to rely so much on satellites. We went from 20 years ago to having a few hundred satellites in space. Now we have thousands of satellites in space. And they're all vulnerable. They're all vulnerable, and we rely on them. Another thing that we saw with this last storm, a year and a half ago, were GPS issues. Now, EASY doesn't study GPS issues per se, but a Carrington event or any type of large solar storm can send these little ripples through the ionosphere. And the GPS signal has to come through our ionosphere. As it comes through and sees these little ripples and changes, you lose lock or you don't have precise positioning. And so we saw impacts to our economy, to people not being able to know where they are. And nowadays, when we're landing airplanes, we're flying things around with our GPS signals, losing that capability can have a huge impact. So we need to be very well prepared. And of course, in the United States, we have something called the Pro-SWIFT Act that was passed a little while ago that really tries to harden our defenses against space weather.
So the next question is from Darkside on YouTube, and they ask, how long will the satellites be in orbit and how fast will they be traveling?
So this spacecraft are for 18 months. They are in the orbit. I think they are traveling 7 kilometers per second, right? If I'm not
that's about 8 kilometers per second. Yep.
8 kilometers per second. So they are going very fast. And, to go over one orbit, as we mentioned, it's about 90 minutes. So we have 16 times that the spacecraft can go on the area of the region of interest. So over the 18 months, we will be collecting a lot of data. Each spacecraft, 4 channels, 3 spacecraft. So simultaneously, we have 12 measurements that we are looking at these Aurora electrojets. And by having the 3 spacecraft, we can see how, because these Aurora electrojets are all the time evolving, and we can understand that how quickly they are evolving, how are they shaping. So having the 3 spacecraft help us a lot with answering that question as well.
Patrick on YouTube asks, what are the EASY satellites made of?
That's an interesting question. So, this different components have different materials, but the body of the spacecraft, it's aluminum.
Okay, and a riff on YouTube asks, what are the scopes for fundamental physics in the EASY mission?
Fundamental physics, right. So heliophysics, which is, again, the study of the sun and its interaction to the solar system, has multiple components. One is the space weather component, the impact on society, and we have that. The other is the fundamental physics component that you just asked about. And we have lots of missions that study fundamental physics. Parker Solar Probe, for example, flying through the solar corona, is studying the fundamental physics of heating acceleration, how the sun gets hot. Magnetospheric Multiscale is studying the fundamental physics of magnetic reconnection around Earth. I would say EASY has studied the fundamental physics of how magnetized bodies interact with the sun. Any magnetized body around the sun, Jupiter, Saturn, any of the planets, any asteroids with comets with magnetic fields, they have the same sort of interaction. They drive currents. The currents are a standard part of any object that has a magnetic field. And so by understanding just that basic interaction here at Earth, we can then look at exoplanets, planets in different stars, and maybe we can use the signals, the kind of signals we see here on Earth, and say, there's a planet over there. It has an atmosphere, it's flowing with currents and things like that. So even though there's a scientific sort of an aspect of space weather, humanity, and trying to understand our interaction, there's really is a very basic principle of how do magnetized bodies interact with the sun.
So Erica on YouTube asks, was any AI used during the project?
Any AI? I'm thinking about it. I know that we can use the future data that we get and use it for, because it's a lot of data. Even the magnetometer, we can use it for data trending. But we did not use any specific AI for this space mission.
Okay.
But really good question.
Banglabar on YouTube, they ask, what if the satellites loses connection?
It happens, actually. It's sometimes it happens, and we just have to try to make connections, send a signal. We don't give up if we lose connection. We'll ask for more communication. So the satellite, it's always talking to the ground station. That's how we talk. And we try to get more time for the ground station so we can have emergency contacts. But it's actually something, especially on low Earth orbit, it's something that the satellites see, and that's part of the planning, that we know that we will see more, like every 20 days, because of especially SAA event, the South Anomaly region that you have the radiation, it's very high. It could easily cause the satellite for a couple hours to get disconnected and lose communications. But we need to be persistent and continue talking to them if they don't, even if they don't want to answer the phone. We have to make sure that they talk to us.
Mm-hmm. Okay, so our next question is Andrew Bennett on YouTube, who asks, will the astronauts aboard the International Space Station have work or missions that coincide with this study?
So I'll give that a shot. It's a really great question. It's really interesting time in our life to have an orbiting laboratory right up there with people involved. The two instruments that I'm aware of on the space station that are relevant to us, one is called CODEX. That CODEX has been up for maybe 2 months now, and it's a chronograph, and it images the sun in a completely new and really cool way. And so from that, we can actually see things coming from the sun. The other is AWE, the atmospheric wave experiment, and that's looking down and looking at things like gravity waves that are affecting the upper atmosphere. So from the space station, those are two that maybe aren't directly relevant, but we'll utilize them in an ancillary sense. There's another mission that just launched, in fact, just a few days before. It's called PUNCH. It's the polarimeter to unify the corona and heliosphere. And it's interesting, that is also looking at the sun. It has a chronograph and a heliosynthetic imager that sort of looks at all the stuff that's coming off of the sun. And what's kind of cool about that is it flies in a similar orbit as EASY, and it's, again, imaging. So it's not designed to measure the aurora, but it's going to be looking through the aurora. And so what they consider noise that they want to get rid of is actually our signal. And so we've been talking to that PUNCH team since inception about how we could use their data to look at the aurora that they will just throw away because it's not part of their mission, how we can use their images of the aurora and link them to EASY. And that's something I'm actually really excited about.
That's awesome that you can, connect with other missions, and there's so much more data to work with.
Right.
So XYZ on X asks, how do you protect the satellites from potential impacts during space weather? Are satellites on the far side of the sun also impacted?
Good question. So I think one of the things that we do, the components that we use, we try to be radiation tolerance. So there is a lot of testing that we do. So the components that we use, they have like flight heritage. So we are very comfortable that to some extent they can support the radiation. But again, the single event upset that happens, it could happen no matter how much testing you've done. For example, Van Allen probe, it was two spacecraft that went to the heart of the radiation belt, but that was designed, and we had a lot of shieldings for that to make sure it protects the spacecraft. But the low Earth orbit, like EASY, they don't have those kind of protections. But it's still, we have a lot of flight heritage, so we are comfortable that they can operate 18 months. And maybe even we go beyond to get extended mission for EASY. I don't know, what was the second part of the question?
Are satellites on the far side of the sun also impacted during space weather events?
Yes, they are all connected. So they can be all impacted the same way.
Yeah, there's an interesting, the last solar cycle, we did not get a large Carrington-style storm back then. But Stereo, one of NASA's spacecraft, was close to the other side of the sun, in a totally different region. And when these coronal mass ejections leave the sun, they fill out a large portion of the heliosphere, the place in which we live, but not everything. And so we didn't see this large CME, but Stereo did. And that CME was moving so fast, it actually went off scale of the instruments. And if that had hit us, that would have been pretty close to a Carrington event. I think that event really woke a lot of people up.
So our next question is from Endeavor to Persevere on YouTube, and they ask, how do you protect the battery from solar radiation?
Larry, do you want to take that question?
I was going to say that's a Nelly question, but okay, how do you protect the battery from solar radiation?
Battery. Oh, I didn't understood the question.
I can answer. So batteries actually are tough, actually, to be honest. There are a lot of requirements on batteries. So batteries, as you know, if you tried to operate your phone or your camera in really cold environments, they don't work very well. We find the same type of lithium battery sometimes that you have. They're space-based, but they're the same battery. And so when it's really cold, they don't work very well. Now, when they're really hot, they don't work very well either. And what's tough about these orbits is we go into the shadow of the Earth and then we're in the sunlight of the Earth. And so these spacecraft have to keep that battery not too hot, not too cold. So there's a lot of design work that goes in and how to either feed it to keep it warmer or to take the power out and keep it cooler. But there's a limited range of where you can operate that battery. We try to very carefully design that spacecraft to keep it in that range.
So Miles on Facebook asked, what is the advantage of using CubeSats for the EASY mission?
I think one of the advantages that we're low cost, the science return, it's very high. I always say the mission was class D. That means you can take a lot of risk, but the science of it, it's class A. We're making a lot of science, new science for the first time. So I think the advantage of it, it's using a CubeSat like Easy Mission. You can lower the cost, you can increase the development time. We had 40 months only on developing these 3 CubeSats on 3 instruments. And I want to thank our partners at Blue Canyon Technology and JPL for their help in developing this mission. And really, I think this is a new way of collecting science in a low cost, fast rate that we're very excited.
So another question on YouTube is, what is powering EASY?
So there are a couple mechanisms. One is the solar panels, of course, that they are, constantly in each orbit. We have a couple hours that the sun, not couple hours, couple minutes that this solar panel is charging, and then the charge gets stored in the battery. So the battery will keep the charge, and when we are on the dark side, that the solar panels are not charging, we use the battery. So it's a very complex system that they have to work together to make sure that the satellite is constantly have enough charge.
Okay, so our next question on YouTube again is, how long does average space weather last for?
You want me to give that a shot? So again, there's different kinds of space weather. It's a broad range of space weather. So a coronal mass ejection starts with a flare. And that flare, if it's pointed in the right direction or wrong direction, can send particles to the Earth. And those can last several days, actually, that we're connected to the sun, and you can see it there, and we're connected. That CME can take about 2 to 3 days to reach the Earth. And then when it reaches the Earth, it causes something called a geomagnetic storm. And that storm is when you squeeze the magnetosphere, and those can last, again, 2 to 3 to 5 days. There comes the CME now, lifting off of the sun. The kind of event that EASY's really designed to study is called a substorm. Substorm are when you see beautiful movies of the aurora, the things that happen very quickly. Maybe they're over in 20 minutes. And so a substorm is about 20 minutes. The storm is about 3 to 5 days. Enhancements in the radiation belts. Again, it depends on what kind. Sometimes during really strong events, we get something really close to the Earth. You sometimes hear people talk about the inner zone. In that region, those can last years. And that's actually really quite dangerous because those are very energetic particles in that inner zone, very close to where our satellites operate. So those are different timescales that you see.
So we're getting a lot of questions on YouTube. Our next one on YouTube is, how long did it take to design and build the EASY spacecraft?
It's a really good question. So for any NASA mission, there is about 2 years before you even propose. You start thinking about this kind of mission, what kind of science you want to take. And after you get selected and you go through the process of the competition and you get selected, Easy mission took about 40 months from phase B. Each phase it has a different name, but the early on that you start the designing till you is making your engineering model, the flight model, do a lot of testing until it gets ready for launch, it was about 40 months, which is a very interesting record for 3 CubeSats and 3 very complex instruments to be on time and on cost to be developed. So we are very proud of that.
That's very impressive. Okay, so we have a question from Krishna on YouTube, and they ask, what is the single point of success of this project, and how will it benefit citizens?
No, I was thinking you might know your requirements right off the top of your head, but I can say that my answer would be different.
Yeah, I mean, there are requirements that we follow, but I think what it's really successful for every mission is the teamwork. You know, the teamwork and communication, that we work together, making sure that we mitigate all the risks. Because at the beginning, when we start these projects, we know what kind of requirements we have and we need to meet. And you always meet obstacles, issues, but the teamwork, how you resolve that, is the key for the success of every mission, that how great the team work together, how hard they work together.
Yes, the main science question of EASY is really looking at these electrojets, the currents that flow in the ionosphere. And the big question that we've developed over the last 20 or 30 years is, what is the spatial scale of these electrojets? The textbook, when I grew up, when I was in grad school in the 90s, the picture they drew were these just lines. It's sort of like a picture you had earlier where you saw the current. They're just these horizontal lines. And we view them as sort of these just long line currents flowing in the ionosphere. But what we've inferred over the last decade or two is that actually that line probably isn't correct. It's probably full of these little elementary, smaller current systems. And our missions have not been able to really analyze that at all. You can't really see them from the ground very well because you're too far away. And you can't do them with a single satellite. You don't see the evolution. So you need these multiple satellites. You need the imaging that we have with EASY to give us these maps and these pictures with the different scale sizes of the current system. So that's actually the main science objective, is what is sort of this middle scale, this middle mushy scale that we can't more resolve? How do they drive the GICs? How do they drive the electrojets? And that's the main science question of EASY.
All right, so we have time for a final question, and this is for both of you. Can you quickly tell me, what advice do you have for viewers who might be interested in helping NASA study the sun and its influence across the solar system?
Very good question. I think the main component is to be curious. Be curious and determined and follow your passion. And always push yourself. I think when you are curious, you want to try to find the answer. It always take you to beautiful places that, you can't ever imagine. And so curiosity, for me, it was very important. I always loved the sun. I always was very interested about the space, but I wasn't sure that I will have an opportunity in working for NASA. So my advice is to young girls and boys, if you are determined and you're curious, you can achieve everything. I'm a model of like a person that was able to be working on the space mission. So if I can, I'm sure you can, make it happen too. And always wanted to learn. For me, like when I finished my high school, I wanted to study electrical engineering and then get my master's and PhD. And it was always because I wanted to learn more. And I think continue to learning, it's a very important key as well.
Yeah, I always love this question because I always ask people, what got you into science? What is your story of how you got into science? And be curious is, of course, extremely important. And I remember just a few weeks ago, I was talking to a colleague in Europe who grew up in Lebanon a while ago and grew up in a very poor area and didn't have a lot of resources. But a solar eclipse came by. And she was living in her house, and there was a hole in the wall, and that eclipse, the hole acted as a pinhole camera, and that pinhole camera projected the eclipse onto the floor of her house. And her dad said, "Get out a piece of paper and draw that solar eclipse." And she sat down, and she drew it, and she had it for years, and it really inspired her to enter science. And now she's a very well-respected planetary science in Europe. But it's such an amazing story because children have this inherent curiosity, right? That we all I'm jealous of them, right? Because we all get jaded as adults and we don't feel as happy and curious. But look at the universe through the eyes of a child, right? And this last storm that happened a year and a half ago, I think all of us were very excited to see the aurora down at regions we don't see it. And I was actually working up at my kid's school, and my wife texted me, says, "Larry, there's aurora outside." And I ran outside, and I happened to see the aurora above my kid's school, Veterans Elementary. There's a beautiful picture of the red aurora right above Veterans Elementary School. And I sent that off to the teachers and the principal at the school. There it is right here. Yeah, it's right there. And they took this picture and they shared it with their classroom. Every student at that school saw this picture. And they had questions about the aurora, and my wife went and answered questions about the aurora. And just something simple like that, a picture that makes it relevant to them, inspires curiosity. And hopefully we inspired a few kids to enter science, to look at the world around you. And it's just simple things like that. Look at the world as children look at it, through the eyes of a child.
That is great advice. Thank you both so much.
No, my pleasure.
Yeah, and thank you so much. Yeah, and thank you so much for joining us to discuss this incredibly important topic and mission. Great, and thank you to everyone watching online. To stay updated on the Sun, follow NASA Sun Science on Facebook and NASA Sun on X. We'll be sharing updates on those channels as well as on NASA's website about the EASY mission and other missions we have studying the Sun. So stay tuned. Thank you and see you next time.